Hello everyone for the August iteration of the Spatial ML seminar series. Today, I'm very happy to welcome our speaker, Taikun Zhang from the University of Toronto. Taikun is a second year master's student in the computer engineering group at the University of Toronto, supervised by Professor Bombets. And his research focuses on accelerating deep learning models using AI optimized FPGAs, which he's going to talk a little bit about today, especially for graph neural networks. And Taikun also studied computer engineering for his bachelor at the University of Toronto and completed internships at Tenstorrent, NVIDIA, and Altera. I've worked very closely with Taikun, and he's a superstar and he's about to graduate. So if there's anyone from industry on the line, I think it's your chance to get in touch with Taikun. So please take it away, Taikun.
Thank you, Andrew. So hello, everyone. Today I'll be presenting my work on a software-programmable neural processing unit for graph neural network inference on FPGAs. And this will also appear at this year's FPL conference. So let's start with a bit of motivation. Graphs are like a popular way used to represent many parts of our world. And as a result, there's a lot of emergence of graph neural network applications due to their ability to process and represent graph structured data. And shown in this slide are just a couple examples of some of the more popular GNN applications for GNN applications. But the trick is it's very tricky to accelerate GNNs because there's a lot of diversity amongst these applications, and this results in many unique requirements for acceleration. So to support a diverse set of graph representations and models of real-world systems, this actually requires a lot of flexibility and programmability. In addition, each application might have its own distinct performance requirements, such as prioritizing either latency or throughput. And additionally, many GNN applications are actually integrated into larger systems, and this requires communication via direct IOs or other customized components. So with all these components, it seems like they match, or with all these requirements, it seems that they match up very nicely to the strengths of an FPGA. So why not use FPGAs to accelerate GNNs? And another question is, what type of accelerators should we build on the FPGA? So there has been a lot of work done recently on accelerating FPGA or GNNs using FPGAs. The state-of-the-art FPGA accelerator for GNN inference, called FlowGNN, they actually minimize latency using two things. The first is that they implement model-specific streaming hardware, and they only process one graph input at a time. And this is ideal for latency-sensitive applications that use a single GNN model and also do not need to process multiple inputs. However, what if the performance target changes and the application requires a different target for performance? This is an example of this is in multi-lidar for multi-lidar sensors in autonomous vehicles, where you may need to process data from multiple sensors at a time. Additionally, a GNN application may consist of different types of GNN layers, and this requires the ability to switch between workloads dynamically. So our research question is, can we build a GNN inference overlay that provides the software level programmability to execute different GNNs, along with the flexibility to trade off between latency and throughput for different performance targets, but still have the competitive performance to a fixed function streaming data flow hardware? And the answer to our research question is that we decided to build on top of an existing high-performance overlay architecture. And in the next couple of slides, I will briefly introduce the NPU. So the neural processing unit is a deep learning FPGA-based accelerator that was designed for the deep learning inference of sequential models and feed-forward networks. It utilizes an overlay architecture that can be programmed with complex and large instructions. And each instruction is actually capable of launching thousands of operations per cycle. And these instructions can be purely programmed through software onto the overlay to dynamically change the workload. But even with the programmability, the NPU has shown to have low latency and high throughput. And in a previous study done by Andrew, we saw that the NPU could outperform AI-optimized GPUs at low batch sizes. And this is a result of keeping these quantized model weights persistent in the on-chip memory and leveraging the Stratix 10 NX AI tensor blocks for enhanced compute capacity. So the baseline NPU architecture consists of 5 pipeline stages. At the heart of the NPU is a very massive parallel matrix vector unit that computes matrix vector multiplication. The second stage consists of an external register file, and this is used to skip the MVU if needed. The next 2 stages are 2 identical multifunction units, which consist of various vector element-wise operations used for deep learning workloads. And the final stage is the loader, which is used to write inputs and outputs to the outside world, or write back any intermediates to any of the register files in the NPU. And now with the brief introduction of the NPU, I'm going to now talk about how we re-architected the NPU data path and its ISA to support various GNN types. But first, we need to actually analyze these GNN workloads to know what base operations we need to support. Because once we can support these base operations in the hardware, we can let the NPU compiler break down GNN models and schedule instructions onto the hardware. So what's in a GNN? Well, a GNN layer consists of 2 parts. The first part is called the low node linear transformation, which basically transforms a node embedding vector using a weight matrix. And this must be done for every single node in the graph before the next step. And these linear transformations can be mapped onto the baseline NPU as a matrix vector multiplication. The second part of a GNN layer is called the neighbor vector aggregation stage. And in this stage, each node receives all the transformed node embeddings from each of its neighbors and aggregates them using an arbitrary aggregation function. And this step is what differentiates different types of GNNs from each other. Listed on the right are some examples of common operations that are required. Within those, some are actually part of more complex functions like softmax. And actually most of them typically require high precision floating point. So how did we re-architect the NPU for GNNs? Well, we first modified the non-tensor ops to use brain floating point 16 precision from Int32. We supported some of these new operations needed for aggregation in the MFUs. We added a 6th stage to the NPU, which computes the stable softmax of a vector. And then we made all the corresponding changes to instruction decoders and the control path just to control these new compute units. And you can find more details of other enhancements in the paper. So I'm now going to go into a little bit more detail about one of the changes that we did, and this is going to be the resource efficient stable softmax. And softmax actually used for graph attention networks, which are one of the more popular GNN models. An important feature of the softmax block is that it's numerically stable, and this just means that there's no underflow or overflow of the exponentiation unit. Also, it supports the interleave execution for up to batch 3 inputs. And this is just another way to say this is that it just matches the data path of the NPU. So I'll go through an example. Hopefully, it will make it much clearer. So if we have a batch of 3 vectors, and each vector is double the length of the NPU's data path width, then as we can see here, each vector will be split into 2 chunks and interleaved with the other 2. So computing this softmax will actually take multiple passes through the softmax unit. So on the first pass, what we do is we let all these chunks flow through the softmax unit and find the max, which we then store in some local storage. And then the outputs remain unchanged from the input. On the second pass, we subtract the max element stored away from every element in the vector. Then we compute the exponentiation and then the running sum for the denominator of the softmax formula. Once again, we have to see all chunks to find the total sum of each vector and store it locally. And in this case, in this pass, the outputs are the exponentiation of the inputs, which will be used on the next pass. And on the final pass, we take a reciprocal of the running sums that we calculated in the previous pass and multiply them with the exponentiated inputs to finish calculating the softmax. So there are many characteristics of the softmax block that allow it to have efficient resource utilization and low latency. By using local storage, we're able to reduce the memory overhead that CPUs and GPUs often incur when writing intermediates to and from memory during the softmax calculation. We can chain base operations of softmax to reduce latency. And finally, by streaming the data multiple times through the block, which is the multiple passes in the example that I just showed, where we can reduce the amount of hardware resources allocated to calculate the softmax of a very large vector. And finally, all these compute units in the softmax block are still software programmable. So now I'll transition into the other half of the NPU, which is the software stack. Previously, users could accelerate sequential models using the Keras library from TensorFlow. And now we've added support for PyTorch Geometric, which is a widely used framework to develop, train, and run graph neural networks. And underneath these high-level frameworks, we have APIs for the NPU, which call model-specific kernels, depending on the layers in the model. And these kernels just consist of low-level memory management, instruction scheduling, and are described using the domain-specific language of the NPU. So the DSL is basically a simple library of NPU-specific functions to implement common operations such as vector load or matrix vector multiplication. And actually, an experienced user can directly use the DSL to reprogram the NPU instead of these high-level frameworks. And this basically gives them the freedom to write any program and run it on the NPU. So the NPU ISA uses a very large instruction word format consisting of individual instruction fields, which are used to control each stage in the NPU. And these instructions are created by the assembler, which groups the small atoms from the DSL and translates them into machine code. And finally, many of these big VLIW instructions form a NPU VLIW program. And now I'll show how we use the software programmability of the NPU to exploit different levels of parallelism in GNNs. And actually, in GNNs in each layer, many of these operations on each node can be performed independently in parallel with others. For example, when I talked about the linear transformation or the first stage of a GNN layer, I said it was just a matrix vector multiplication. And this is done for every single node in the graph. So I'll go through an example of how we can parallelize that stage using the tensor blocks. So if we have 3 graphs, each with 6 nodes, one approach that we can do is to process the same node from different graphs in parallel. And in this case, all 3 graphs will finish processing at the same time. We can also refer to this as batching 3 graphs. The second approach is to process different nodes from the same graph in parallel. And in this case, when we'll process all 6 nodes of graph 1 before we process graph 2 and graph 3. These 2 approaches actually result in different performance trade-offs. By batching graphs, we are able to achieve a throughput optimized workload, whereas if we focus on processing one graph at a time, we actually get a latency optimized workload. And this is actually a new feature of the NPU that allows users to tweak their workload to best suit their application's performance requirements. And in addition, the benefit of this approach is that these performance targets are actually compiler flags, which are given to the compiler at compile time. So any user can change these flags to see how these methods of exploiting parallelism will change their application's performance. So far, I hope I've made a case for the NPU's unique flexibility. Now let's see how the performance of the NPU matches up to other accelerators. So we first evaluate our NPU against a RTX A6000 GPU and FlowGNN using 3 models across 5 data sets. Each model consists of 5 layers and an MLP output layer with an embedding size of 100. We also evaluate our NPU against a Verso-based GNN accelerator utilizing AI engines with 4 models across 3 data sets, and each model has 2 GNN layers and an embedding size of 16. But first, we do a large design space exploration. And this is just used to determine the best NPU architecture parameters for our device across our suite of workloads. And the workloads that are in the suite are just the sequential models from the previous study, as well as the new GNN models for this evaluation. So after implementing the NPU and running it through Cordis, we see that we are using around 50% of the tensor blocks in ALMs and a lot more BRAMs at 80%. However, we are still able to achieve Fmax of 300, and we do this by having an optimized microarchitecture. So first, I will do a comparison or do a performance comparison of the latency and throughput optimized kernels of the NPU, just to see how it's changing the compiler flags affect the performance of the NPU. As we can see, the throughput optimized kernels actually provide around 1.8x higher throughput compared to the latency optimized kernels. And likewise, the latency optimized kernels can actually achieve 1.6x lower latency compared to the throughput optimized kernels. So choosing the correct kernel for your application or the correct performance target for your application can have big trade-offs in performance. And now we add the numbers for the GPU and FlowGNN. The first thing that we see is that the NPU achieves significantly higher throughput, on average 5.8 times the GPU and 7.8 times of FlowGNN. And comparing the batch run latency results show that both FlowGNN and the NPU are much faster than the GPU. And as well, we see that the NPU is using the latency optimized kernel is actually having comparable latency on average to a streaming data flow architecture. We also measure the energy efficiency using a power meter that's connected to the NX board while we run the workloads on the mole HIV dataset. Our NPU achieves on average 900 times the GPU and 3.6 times flow GNN in terms of energy efficiency. And now when we run the models on some larger graphs, we actually see that the NPU achieves 1.6x higher throughput on GCN and GIN models, but similar performance on the graph attention network versus flow GNN. And vice versa, we see the same trends when measuring when comparing the batch 1 latency. However, something interesting is that for the HEP10K dataset, flow GNN actually outperforms NPU on those graphs and workloads. And this is because due to the nature of the structure of the graphs, in each graph of the HEP10K dataset, there's actually each node has a very large and very high degree, which the NPU doesn't scale well compared to flow GNN. However, both flow GNN and NPU still outperform the GPU, proving that FPGAs are a good choice for accelerating GNNs. And we also compare the NPU against an accelerator on the Versal device, which uses the AI engines. So if we compare the core compute latency, we actually see that the Versal accelerator outperforms the NPU on all workloads and data sets by a significant amount. However, this is actually not the full picture of the system. The Versal accelerator pre-processes graphs to schedule the sparse portions of the graph onto the spatial fabric and the dense portions of the graph onto the AI engines. So if we add in the pre-processing and the data transfer overheads, we see that the NPU can achieve 3 to 12x lower end-to-end latency on the Cora and CiteSeer datasets. However, for a larger graph like PubMed, the benefits of pre-processing outweigh the overheads, or the benefits of pre-processing outweigh the overheads, and we see that the NPU achieves only 0.66 to 0.95 times the latency. So now that I've shown how the NPU performs compared to the competition on standard benchmarks, let's take the NPU and show how its flexibility and high performance allows it to enable new applications in the communications domain. One area where FPGAs are already widely deployed is actually in the communications domain. But first, a bit of background, as I'm sure that many of us are not experts in the communications domain. But in today's 5G wireless networks, transmission speeds are down to the unit of microseconds. And a key component of enabling the low latency and high throughput of these 5G systems is multi-input, multi-output attendance scheduling. And these scheduling algorithms, what they do is they decide the best pairing between requesting users and available frequency bands of the antenna to reduce interference. However, as the number of users grows beyond a certain number, traditional methods do not scale well in complexity. And recently, GNN-based schedulers have emerged as an alternative to traditional methods. And the reason why GNNs match very well to the problem is because these wireless networks are easily represented as graphs. And in a GNN study done by Intel Labs, they're actually able to reduce the complexity by over 90%. But still achieve within 94.5% accuracy of the best possible solution using a GNN. And I'll go into a little bit of detail about the GNN network that we use. It's actually very unique. So it actually uses 3 graphs and 3 different GNN layers Each graph and layer represent a part of the wireless network. And then after each layer, after every layer, the sum of the three GNN layers are summed up. And we actually have to repeat this layer for all bands or all frequency bands of the wireless network, which requires high throughput. So we need to batch these graphs when we're doing inference. So we run a 4-layer GNN-based MIMO scheduler with an embedding size of 8, as described in the paper, onto a batch 24 NPU configuration. And we use a throughput optimized kernel to get the best performance for the workload. And as we can see, for up to 100 users in the network, we are able to achieve less than 80 microseconds in MIMO scheduling. And this is actually well under the 1 millisecond transmission speed constraint for 5G networks. But we also can provide high throughput, so we can do the scheduling for all 24 bands simultaneously in under 80 microseconds. And this case study shows how the high performance and flexibility of the NPU can enable very unique workloads. So in conclusion, we introduce a software-programmable and high-performing NPU overlay for GNNs with the flexibility to target throughput-oriented and latency-oriented use cases. On smaller graphs, we average 5.8x and 7.8x throughput compared to FlowGNN and the GPU, with comparable batch 1 latency to FlowGNN, which is a streaming data flow, which utilizes a streaming data flow architecture. We also achieve 3.6x and 900 times the energy efficiency compared to FlowGNN and the GPU. And on larger graphs, we can achieve 1.8x lower latency on GCNs, GINs, and having similar performance on GATs versus FlowGNN. And because we don't pre-process graphs, we can achieve 3 to 12x lower latency for Cora and Sightseer datasets against the Verso accelerator. So to conclude, the flexibility and high performance enable new applications. And one example is the MIMO antenna scheduling that is used for wireless communications. And thank you for listening to my talk, and I'll be glad to take any questions.